there yet?
No, I'm saying watch your mouth.
Let it read off.
You log in?
Chop, chop,
Hank?
Do you think I need to today?
Yes. They told me what the problem was. We'll be logging in a lot.
Okay.
I got two Sam, a Dennis, and a Jeffy.
Okay.
Jeffy. It's Dropbox. It's Dropbox.
Oh, Dropbox?
Yeah.
Really?
Yeah.
Oh my goodness.
Yeah, I've got a Dropbox account because of a education project I'm working on. And it's the most unorganized piece of junk you ever saw. All the contributors just throw stuff. I mean, it's highly structured according to each individual, but there's crap all over the place.
Okay.
And it's an infinite account.
Not too good.
Don't worry. So they were going, wow, he did bacon. Like, no. Okay, thank you. And big hug. Or not. You guys remember Red in Arizona? Somebody told me yesterday that my obscure references annoy them. It wasn't you, Jeffrey.
Okay.
But maybe next time. Maybe
What is that touch roll thing?
if I knew I'd tell you. Since I don't, I won't. Texting your woman. All right. Picked the wrong week to quit sniffing glue. You don't remember that?
What?
I picked the wrong week to quit shooting heroin.
Okay.
That was great. Especially with such a respected actor, Lloyd Bridges. You're not someone who studies like 70s sitcoms or anything, are you? All in the Family, you know, that was one of the greatest TV shows in history, right? The guy they cast as the lead was absolutely perfect. But they actually cast somebody else, and he turned it down, and spent the rest of his career scratching his head. Also read where the guys who were the leads in Miami Vice almost lost out to two other guys. They would have been a completely different, I don't know how to explain it.
There's so many cases like that
Yeah.
where they were hoping for somebody else.
Well, do you remember the father in Talladega Nights? Ricky Bobby's father?
Yeah.
Yeah, and he was also Lundberg in Office Space.
Yeah.
He was supposed to be Crockett.
Was he really?
Yeah, but he lost in the final round.
He comes to such a dry humor role these days.
Yeah, well, he said that his first humor was Office Space, And then he never took Office Space seriously. He thought it was just another movie and, you know, be a check mark in his career. And he says now everywhere he goes, people are like, yeah, that would be great. Can you give me those TRS
Give me
forms?
those reports.
That was a good movie. Okay, so I'm having a little bit of a, what do you call it when you have an internal battle? Dilemma. Thank you. Very good. My dilemma is which two problems to assign. I think I got the kinks worked out. I threw a lifeline to somebody that I worked with quite a bit. I wanted to give you good, and he wanted to give you evil. I think we'll give you evil. It has the net effect of doubling your work, which is actually a good thing. I'm exaggerating. It's a case that is severely affected by rates and a build-up case. So if you ignore the rates, then you get one interpretation. If you don't ignore the rates, then you get a completely different interpretation. It's probably a good case to use. I had a, hey man, you didn't reset flashes on me. What am I supposed to do with these?
I don't know.
There isn't enough love there.
Give me an A and got some behind it.
What I'd really like to give you an A for is solving some important problem in the universe. Can you do that for me?
Possibly.
You think we're going to have anybody else?
No.
You're J2, right?
Yeah.
No.
Not his forehead.
No, he's Johannes. Or we could call him Johnny Boy. Every time my daughter wants to make my son insane, she calls him Joanna. His name's John. And I don't know where Joanna comes from John, but and I know this is wrong and I shouldn't tell you, but for years, every time he would not act the way I wanted, I would call him a girl's name. And it finally came to a head whenever he became bigger than me, and I decided I'm not going to do that anymore.
Your son?
It was a conscientious decision, yes.
What? Wow, how big is he?
I might be able to find a photo of him.
How old is
He's 15.
and he's big, he's big. Wow. That's
Yeah.
a very...
Yeah, my wife thinks he
Scary.
stopped growing, but now he rests his arm on her, you know. And it's like those movies where a little tiny woman has, well, she's not a little tiny woman, but and it's recorded too. Oh, God. But let's just say he divorced her, yeah. I'll leave it at that. He's a good kid, though. I just got to get him off of video games. He's always had this addiction nature, where he does something and he really gets into it for a while, and then he switches to something else. For example, when we bought him a Game Boy, he just stared at it the first year, and then the next year they were inseparable. You know, it's like he had to carry extra batteries and that sort of thing. I don't know. Just happy to play video games all day. I mentioned to him that people don't get paid for playing video games.
They do.
He just went right over his head.
You can if you're really, really good.
Yeah, thanks. Now shut up. Okay.
I mean, he is close to Singapore.
Yeah, he does play, some of his buddies are in Asia and, you know, wherever somebody's awake. You know, they play those.
Yeah, it's not
Is
really...
it Minecraft and
Minecraft won't get you anywhere.
all these war games and that sort of thing.
Got to play soccer. You play soccer?
I don't play games because I don't want to waste my life in front of the computer. Dennis, can you help us here? Throw me a lifeline?
What do you want?
Where's the page? You were supposed to bring it. You like my new style? Yeah. These are my big eyes. Okay, so what we're gonna do today is cover very quickly the reservoir models, because this is gonna apply to both, well testing and production data analysis. And if I talk a little too staccato today, I just had a 2-hour webinar with 400 people listening in, so. And I was watching them type questions. Fortunately, I didn't get them all, but it looked like a blur, like one of those old 60s things where the computer is talking and it's just streaming across the screen. Somebody made a record of it. I don't think I'm obligated to answer them, so probably won't. Okay, so the natural state of a reservoir engineer is to assume that the reservoir is a bounded circular reservoir. We have 3 options. We can have an infinite outer boundary case, we can have a bounded circular reservoir, and then we can have the constant pressure case. Constant pressure is what? Then
Can you get rid of the personalization?
Do you want the taskbar to be locked?
what?
The taskbar is blocking the.
Right click on the taskbar, go to properties. Go to properties.
You still have those.
And then click the auto hide.
Perfect.
That's fine. Thank you. All right, so steady state. What do we think of steady state?
It's fleeting. It doesn't exist.
It's not a practical condition. This book was written in the 60s. It's a great monograph. It's the first well testing monograph. And in fact, it's the first monograph ever written. Matthews was a mathematician, I think. And I know Russell was. What was Russell's final job at Shell? He was president. So there is a technical path. Shell, U.S. Shell. Okay, so we're basically going to talk about the infinite reservoir case and the bounded circular reservoir case. The infinite reservoir case is pretty much PTA, and the bounded circular reservoir case is PA. I mean, we're not going to really see that application. Looking at it from the top, the flux is coming in like this. So we consider that, I know my arrowheads are terrible, like that. Then, since you took 620, why don't we allow a particle to do this?
You can do that, but we just don't.
First of all, we don't let it.
Yeah, we don't.
But second of all, there would have to be some heterogeneity. There would have to be some preferential permeability path where it would turn that way. Otherwise, the path of least resistance is a straight line. Okay. Now, we do also not have a vertical component. Why don't we have a vertical component? Well, if we had partial penetration, that is, that the well was not perforated at the bottom, then there would be a, like, you like how I drew that, where it makes a zigzag, it doesn't really do that, right? But something like that, and there would be a Z component. So we eliminate the Z and we eliminate the tangential component, and all we consider is radial. I have a student who's working on a project to reproduce the crushed core permeability measurement thing, which turned out to be a lot bigger problem than I ever imagined. But he's a very bright fellow. And what he did is he took spheres, and modeled like a bundle of spheres or a package of spheres. And so in that case, you'd have spherical flow, but it would all be convergent. There wouldn't be any tangential elements or anything like that. The tangential elements and the vertical elements usually come into play when there's anisotropy, that is, if there's a permeability reason for it to do this. Okay, any questions about the models themselves? And the reason I stepped back and did this is because you guys have been struggling, no offense, but you've been struggling with the sort of the background in reservoir, and I wanted to make sure we did cover this. This is the most fundamental reservoir model we'll ever talk about. And it has, as its solution, as you can imagine, the infinite acting case, the pressure drop is proportional to a logarithm of time, and the finite acting case, the pressure drop is proportional to time. Okay. That's how that works.
Is there a reason why you're separating the two models into distinct PDA and?
Well, most of all, in terms of PA, we're going to be looking at long-term data, and PTA, we're going to be looking at short-term data. Very good question. Thanks for clarifying. My brain is really going to have some gaps today. So stand number 2, or stand number 1, did you get enough sleep last night?
Mm-hmm.
Yeah. What's that like?
What else is that like?
Yeah, what's it like getting enough sleep?
You don't feel sleepy when you wake up?
Right. So there's only one of me. You're looking at me, there's only one. I'm looking at you and there's like 5. I'm talking to the one in the center. Okay, just making sure. So I turned 51 on Thursday, right? And I was telling someone that next year my life will be half over. I've deemed that I'm going to live till 103. Do you think you can do that? You can say, we're going to do that? It's going to happen.
Sure.
Yeah. Dennis, how do you want to die? No, nothing.
I had a thought of that,
Right.
yeah.
Yeah. I want to be shot myself. That's my culture. But probably what's going to happen, the last thing I see will be a frying pan wielded from my wife. If you see Made in France across my forehead, you know, when I'm at the funeral, you'll know it was a frying pan. Okay, so the other thing we have to talk about is where is the well located and what the pressure profile looks like. The actual solution is not a logarithm, right then? What is it? It's the exponential integral. And without any complications, the exponential integral is approximated by the logarithm after a few minutes, seconds, or hours.
Minutes.
Yeah. At the most minutes, probably most likely seconds. So, and with well-bore storage, it's irrelevant then, because there will be an effect that lasts into hours. And you can see what they're trying to explain with this is there's exponential integral and the log approximation are the same. Okay. So what about any questions about whether we assume that the well is a line or a cylinder? Everybody's okay with that? It's okay for the back rows that we're using this approximation. As a math major, are you going to be able to sleep tonight knowing that we use a line source approximation as opposed to a cylinder? Yeah, I thought you'd get over it. Yeah. Okay. Does it ever matter?
No.
Yes. The only time it matters is whenever you're looking at 2 wells and you're looking at pressure distribution in the reservoir. So the logarithmic approximation, we talked about that the other day. It has to curve the pressure profile. It can't be perfectly straight. And so that's when we need the exponential integral. When you start, it's an R squared over T formulation, or T over R squared formulation, however you want to look at it. And therefore, whenever radius is the variable of interest, then you're going to have an issue with the logarithm, or at extremely small times, you'll have an issue with the logarithm. But other than that, everything's good. For practical work in PTA, no problem. It's raised an interesting question, though. So, who wants to invent something new? Johanna? Yeah? So, if you look at the literature, there was a paper that came out in the early 1980s on how to calculate some really early time behavior, and the guy was using the derivative. And he was using the exponential integral form, which degenerates into an exponential times another function. It's not a constant. It's not 1/2, for example. It's 1/2 times an exponential decay. At small times, what do you think that exponential decay term is? It's just 1. So, you know, he made a methodology that was supposed to make a straight line plot. It was 1 over T. So, what do you think happened? It didn't work. But it's still kind of a clever idea. He just didn't realize that you didn't need the exponential integral at very early times. The theory says you do, but the practice says you don't. And I know you're all going, what the hell are you talking about? All of his points were slammed up against one side of the graph. I mean, like, the whole cloud was just on one side, and the reason was because the function didn't matter. As far as the solution thought, it was a constant. Interesting diatribe. Yes?
You said that, it doesn't matter to PK analysis, but the presence of the wellbore will drastically change the pressure, profiles in the near wellbore.
Sure, but whether it's a line or whether it's a cylinder really only matters in the outer region. But whether you use the exponential integral, the log approximation, or the cylindrical source solution, there's a variety of reasons why. The cylindrical source solution actually has a non-decay early time behavior. What does it look like? The cylindrical source is actually a square root of time behavior. It's an artifact of the solution. So it's very, 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 very early time. Rather than looking like a logarithm, which just goes to zero, this thing actually has another characteristic behavior. I don't have a graph of it, but suffice it to say, unless you're really, really interested in this, it's probably not important. Thank you. All right, so we have two possibilities for the skin factor, and this is what the pressure profile is supposed to look like in the formation. Okay, let's pick on somebody. Dennis, what's your least favorite household activity?
Doing laundry.
Okay, well that's easy. Just throw it in the machine, put some soap in, come back a little later and put it in the dryer and turn it on.
Just remembering
If
to
you've
go
done everything right, your clothes aren't all one color. Okay.
just remembering to go back to it.
Oh, that's it. Okay.
On the alarm.
Anybody else have a non-laundry related least favorite thing? Very good. Yeah, I'm not a real fan of that myself. I'm also a little strange about dishes. I like to actually clean them. In New Zealand, they leave the soap on them because they were all taught that that's okay. Where I was going with this is, do you think we could have a special kind of paint where on one side of the paint the pressure is one value, on the other side of the paint the pressure is something else? Could we do that? Okay, so what's happening here is that at RW plus, we have this point, and at RW minus, we have this point. But actually, it's not that point because it drops straight down. Okay. So there's a magic membrane that on one side of this thing, the pressure's 100, and on the other side, it's 10. Okay. That's okay. Your brain processes that. There can be a membrane that does that. Everybody got that? Okay. What about the opposite? What about, here's the profile in the reservoir, here's the pressure R plus, and here's the pressure here at R minus. How did that happen? Well, that's some really magic paint, right? The pressure went back up. Facility? So what happens if you have a process where on one side of a valve the pressure is higher than the other? Do things flow from low to high? Sorry, what was that, John?
I don't know.
Yes. So how does this work?
It works.
It can't work. It can't be real.
No.
So there's got to be a trick. It's a mathematical trick. Mathematically, we're allowed to do this. But physically, this isn't consistent. And what actually has to happen, as the author is alluding to here, is that there must be an actual profile that's up here. The pressure cannot have a magic membrane where it jumps. Okay? So it's easy to understand damage. Okay? But the only way you can have stimulation is to actually alter the reservoir. You cannot have a magic valve or a magic membrane where the pressure on one side of the membrane where flux is coming across is lower than the pressure on the other side. That ain't gonna happen. Or if it does happen, please tell me how. And don't give me this electrochemical gibberish that I know you're thinking about, right? There's some chemical potential that somehow allows something to go one direction and, be higher. Don't try your Jedi mind tricks on me. It ain't gonna work. All right? But mathematically, we can use a trick to do this. And the way we're going to do it is we're simply going to assume that the pressure drop through the skin is a constant, and we're going to represent it as what? Well, we already talked about this a little bit. We're going to allow the infinitesimal skin concept to be valid. So mathematically, we can trick the equation, the logarithm, into doing this. Okay? So if you were going to trick the logarithm into doing this, what would happen is that this pressure profile actually does this, okay? So, and I know this is exaggerated, but what you would do is you would move this point over here. So damage means that RW apparent, okay, well, that's the wrong way to write it. So let's say the apparent wellbore radius, RWA, is very much smaller than the true RW, right? I can use a projection of this profile and simply move this point over onto that projection, right? Mathematically, I can do this. All right, by the same token, and it's a little bit more obvious here, I can move this projection over here. So here, RWA, the apparent wellbore radius, is very much larger than RW. But of course, that doesn't really, again, make sense, but we can make it do that. Again, this is just a trick to allow us to have the skin factor as a component in the system. Yes, sir.
Yeah, but what about like wormholes and phase dissolution?
Okay, stop all that. Okay, those are physical alterations to the system. That is a physical mechanism where you have an alteration and you can represent the skin factor physically. This is a mathematical mind trick, okay, because it's a logarithm. You okay with me on this, Tim, too? Because it's a logarithm, we can take something like a log of, let's say, AT plus S, like that. And what do? Or let me be more specific. We can have a logarithm of AT over RW squared, that's its variable name, right? Plus S. Now, because it's a logarithm, how would you cheat this thing? Anybody?
Explanation.
Sorry?
Make explanation.
Okay, so you have log of AT plus log of 1 over RW squared plus what? Log of E to the S, right? Okay, so then how do we merge these two? There's actually a 2. Well, this is 1/2, so this would be 1/2, 1/2, 2, and a 1/2. Okay? Is everybody all right with that? Okay. So how do we merge them together? This is going to be log of e to the 2s over RW squared, right? Or if RWA is equal to RW e to the minus s.
Where does the half of it A and T go?
sorry, I'm not gonna worry about them, they'll be here. The A, these are just a constant, 1/2. Okay, it's still there. We're gonna say that y is equal to this, equal to that, equal to that, everything's still the same. Sorry. Minus 20, Genesis minus. I might have left out a couple of steps, I didn't. So RWA is equal to what? RW e to the minus s, right? When I move this downstairs, okay? So there's your apparent wellbore radius. So here we have a positive pressure drop. So the skin factor is positive, therefore RWA will be smaller than RW. Here we have a negative pressure drop, negative skin factor, so here RWA will be bigger than RW. It's a mathematical trick. And all it really allows us to do is just represent the skin factor in this way. It does not give us a direct tie back to the problem, like the wormhole or like the permeability alteration problem. What's the problem with the wormhole problem? What's the problem with the permeability alteration problem? You have to know the dimensions. You have to know all the information. Here, all I'm saying is I don't know what comprises the skin factor, but here's how I'm going to use it. Okay. All right. There, everybody. Okay, now we're going to look at fractured wells, and this is a single vertical fracture. Okay. This was first solved in 1981, right? Well, the original problem, not with these authors, but the first time it showed up in petroleum literature was 1974. Wrong. It's in the 1960s. There was a guy by the name of Pratt, and Pratt was showing the incompressible case. He derived the incompressible case, but actually Carswell and Yeager had already done this too, for heat conduction. So I'm just giving you an idea that looking at a slit or something in the reservoir is actually quite an old problem. Now, how do you go from having a slit in the reservoir to having a physical volume in the reservoir? Let me ask it a different way. Dennis, do you remember how we handled this? We took a line source vertical well, which was over here, and we integrated it from XF to minus XF, right? Yeah. And when we did that, we created what? A plane. Okay, so we integrated a well, a vertical well, to complete a plane. Okay? Now how can I take a plane and yield a box?
Integrate by height.
Okay. Same way we did the other, which would be the integrated depth. Okay? So this is vertical well, this is a fracture. For an A in this course, Abhishek, what is this? Horizontal well. I should never say well, I'm sorry. By the way, how did I get to the vertical well? Started out with a point. Started out with a point, integrated to a line, integrate a line into a plane, integrate a plane into a parallel pipe. So this is exactly the progression in petroleum engineering of how we develop these different models. There's a generic approach to this, which frankly I really am not familiar with. I don't try to do these kind of problems. What's it called? Screen function. ring function. Okay. And what this is it allows you to move between geometries by integration. Okay. So scratch all this, that's sort of petty 620 stuff, but I need you to know it anyway. So how do we derive a solution for a fractured well? I just told you, even though we're going to ignore it. Now they did something different, and Dennis is right. So is Abhishek. They generated a plane for the fractured well with a finite-conductivity, FCD. Why? Because this parallel pipe, it has width. This one, for infinite, for FCD equals infinite, it doesn't have any width. A particle of fluid enters here and just magically ends up at the wellbore. But here, a particle of fluid enters and it has to pass through the medium. So we can create a variety of different things. In this case, we're going to create a finite conductivity slab, and that'll be our fraction. Anybody want to tell me what the problem with that is? You now have a reservoir inside a reservoir, right, Abhishek? That's what you were thinking. Before, when you had an infinite conductivity plane, that's okay, you can work the math out. But when you have a reservoir, a slab reservoir inside of another reservoir, what's the problem with that?
It's got two different systems that.
Okay, very good. And you can write interface conditions, but we're going to talk about this in a second. Next. Whichever one of you wants to go next.
I'd say the same thing, dual porosity system.
Okay, it's not dual porosity because they're two different reservoirs connected to each other. The connection would be like a dual porosity or dual permeability system, but they're actually different geometries. The fluid has to turn an angle to get in and to go, which is actually how Lee and Brokenbow derived their approximation. But what I'm getting at is, if you're going to do this rigorously, you have the outer reservoir and you have the slab or the slit that's been placed against it. Where's the weak link?
The connection.
They both, okay, the connection, the interface connection is fine. But a particle of fluid that comes out of the reservoir goes into the fracture, and what happens?
You're imposing an entirely different math model.
All that's true, but what happens?
So regime type, like it changes?
All that's true. I'm trying to give you an idea. If I enter the fracture over here, is that the same thing as entering the fracture over here?
Sure.
No. Because this is a completely different reservoir. The pressure drop will be greater here. So there will be a distribution of fluxes in that slab. How do you calculate a distribution of fluxes? Uh-oh. You guys got it? You don't have to understand it, but do you conceptualize that you have an inner reservoir and an outer reservoir, and in order to balance the mass in the system, the flux distribution in the inner reservoir is going to be variable. I'm not talking about the overall production, I'm talking about the flux going through the system. So the way they handled it was both clever and straightforward. And this is a classic Cinco and San Diego case. They put the fracture inside. The way they handled it is they broke the fracture into pieces. And like I said, it has a separate flux distribution. So you have to solve this independently of that. Or I guess you'd say interdependently. So the inner reservoir, think about a reservoir simulator. The inner reservoir has one distribution, the outer reservoir has another. So this is going to end up, no matter what you do, this is going to end up being a numerical solution. You cannot presuppose the flux distribution. That's the problem. So this was like the biggest pain problem in petroleum engineering for quite a while, maybe 5 or 10 years, because everybody wanted to use it. And it is slow as slow can be. We first moved into this building in 1990. We had Macintosh maximum speed computers in this room, that room, and so on. And you'd come in and you'd make a run, and for 300 points, it would take 24 hours. Imagine that nowadays. So you had to be really careful how you set this up. This is a very slow solution. It's analytic. It's highly, you want it to achieve a high degree of accuracy. So it's a very slow solution. Yes?
Does this have any bearing on reality then?
Of course. This is the real solution. This is the real case. The fracture has finite permeability or finite conductivity. The non-real case is to assume that it has infinite. And the reason that infinite is so easy is because there's no pressure drop in the fracture. The reason that uniform flux is so easy is because you assume that the fracture that you create, you can still treat it as a plane, that if you put a device on any point on that fracture, the flux entering is the same everywhere. Hence the name uniform flux. But the real flux is not uniform. It's something else. And you can see the map of the flux here, XD and QD, XD and QD. You can see the map of the flux. It varies with conductivity and it varies in time, as you would imagine. Okay? You're not going to be tested on this. I just want you to understand that the finite conductivity solution is not your friend. It is a very tough solution. Okay, so we go back one slide and we look at the different flow regimes. All right, I know that I'm going to get in trouble for yesterday, but remember speed? Okay? So now we're looking at the fracture. It's very high permeability. I'm looking at fracture linear flow. I'm going to go from here to the wellbore. All right? The only thing the reservoir, the fracture is the reservoir. What's the flux, or what's the pressure distribution, or what's the geometry of the problem if I'm only looking at a slab? It's linear flow. Doesn't matter how fast it happens, it's linear flow. And that's what we're looking at, the fracture linear flow. How fast do you think it's going to take a particle of fluid to go from here to here? Hours, seconds, minutes, days, decades, weeks, months, years, what? Maybe minutes, but definitely seconds. Okay. I mean, maybe if you're thinking about, a mile long, or let's say a kilometer long, maybe it'll take a little bit longer. But all the flux is in that fracture. So it's going to happen quick. You're never going to see fracture linear flow. Let me repeat it. You are never, ever, ever going to see fracture linear flow. It is a very early time effect. Sorry. It's only for very early times. Seconds. Minutes, maybe. We have storage. What happens? It's gone. Forget it. You'll never see it. All right. Next is what's called bilinear flow. In bilinear flow, the fracture has depth. It has permeability. So a particle of fluid has to go through the fracture. And while the particle of fluid is going in the fracture, all these other particles of fluid are coming into the fracture. So you've got fluid going through the fracture, fluid coming into the fracture. Perpendicular, so what it becomes is this part would be square root of time, and this part would be square root of time. What happens when you have two square roots at oblique angles? Okay, that becomes square root times square root. And that's equal to 4/3. Okay? That's where that comes from. Now, will you see bilinear flow?
Yeah.
Yes, no, or maybe? Yes, no, or maybe?
Yes.
Maybe. Okay? When will you not see linear flow, Jackie? Help him out, Iverson.
When will we not see linear flow?
Not bilinear flow. bilinear flow? When will you not see bilinear flow?
Conductivity is high.
Exactly. Perfect. You got this. Good. So if you see bilinear flow, it means what? Low conductivity. So the if then else, this is low FCD. In contrast, this is high FCD. It's that simple. It's binary. Is there something in the middle? Yes. But like as not, you're going to see one or the other. If you're in the 5 to 10 range, things get a little fuzzy. Coming out of quarter slope into half slope, it might not look like much. Add storage to that, and what's going to happen, Dennis? Are you ever going to see it? No. So would you rather have 2 pressure transient assignments or a pressure transient and production assignment?
You went with touch on production.
I know, but we're going to go tonight and tomorrow. Favorite action figure?
Cobra?
I was thinking more Flash Gordon, but
Ted.
you guys are too young to remember Queen. All right. So high FCD for formation linear flow, low FCD for bilinear flow. What about pseudo radial flow?
If it's a shale, it might take
Okay, so
not in our lifetime.
permeability probably on the order of greater than 0.05117. We'll be generous and say 0.01. I think it's going to be higher than that, frankly. You might see it. Definitely, if permeability is greater than 0.1, you will. So today, I get a question after the webinar that this Figler, and it's all these small fry companies, no offense, they have a reservoir that's 0.2 millidarcy, and they want it to be classified as unconventional. What do you think? It's going to be a hard sell. 0.2 millidarcy is practically, high stuff for us. We're typically looking at 10 to the minus 4th, 10 to the minus 5th, 10 to the minus 6th, not 10 to the minus 2 or 10 to the minus 1. Each one of those is a decade shift, factor of 10. So something that flows at 0.01, it'll be 10,000 times less at 1 times 10 to the minus 6. It'll be 10 times more at 0.1, 100 times more at 1. It's a direct relationship. Okay, so as always, when somebody comes up with something new, somebody has to sit out there and throw stones at it. So what happened was, after Cinco and Samaniego produced their solution, you guys remember green eggs and ham? How did it go? I do not like them, Sam, I am. I will not eat them on a train. I will not eat them in the rain. I will not eat them in, remember that? Okay, no? Nobody wants to admit it, but, okay, so they had a couple of papers where people came along and said, we don't believe in finite conductivity. It's actually a choked or a damaged fracture. And Cinco and Samaniego said, no, you don't understand the problem. You've made a fundamental error in your understanding of what we did. Our problem is that the fracture itself is the cause. They were saying, no, the problem is that there is an outer zone, a skin that's causing this, or there's a choke here. Clever, convenient, and wrong. Johannes, how do you know it's wrong by looking at it? Stare at the two graphs. this is an infinite conductivity vertical fracture, right? No problem there. This is a finite conductivity vertical fracture. No problem there. One has low conductivity, the other has high. The pressure drop for the low case is higher than the pressure drop for the high case. Okay? So then, what happens is somebody adds ADD, a pressure drop, to this case. And what happens? It's a logarithmic scale. So it's off by a constant. What does a constant look like on a logarithmic scale? Well, I mean, it's a constant, but what's a constant plus a function look like on a logarithmic scale? Well, I'll give you a hint. You're staring at it. So it's actually this plus a constant. So it's the delta D linear flow plus a constant. That's what they're showing here. Now this is not Cinco and Samaniego trying to prove that the choke fracture or the skin damage fracture is the same as finite conductivity. They're actually trying to disprove this. And how do they do it, Colin? They just simply point out that it doesn't look anything like the other one. It's supposed to look like the blue line, but it actually is the green line. And I know in the back of your mind you're saying, in this cartoon, okay, in this cartoon, the blue line and the green line could get closer. They could marry. That's fine, except this is a constant skin factor. So what happens when you take the derivative of the green line?
It's just,
What's the derivative of the green line? Is the derivative of the green line going to be the derivative of the blue or the derivative of the red?
the right.
Just again. Correct. So when we eliminate the constant, when we simply take the derivative of this, it goes away. There's no way, other than by a coincidence, that the choke fracture or the fracture skin would equal the finite conductivity case. So that's not an acceptable proxy. That's what they were trying to say. All right? Now, can we add a skin to the finite conductivity case? Of course. And that's a whole other story. That's going to complicate matters a bit. Now, here are the solutions for the infinite conductivity and uniform flux cases. Dennis, do you remember these? Did we derive these? What does it tell you for linear flow? What are you going to see? Square root of time. Long time solution? Logarithm. So at long times, the fracture case looks like a radial flow case with a skin factor. Sam 2. Is the skin factor going to be positive or negative? Okay, so you're saying that the fracture case, which has this conduit out in the reservoir that will produce a lower pressure drop, will have a positive skin compared to the actual case? No, it'll be a negative pressure drop. It'll be a negative skin. All right? So in actuality, we'll have to add a negative number to these if the skin, if you want to characterize it by that. What's all this other mathematical gibberish? Just so we're selling it, right, Dennis? All right. We'll derive all this in 6-1. I am definitely assuring that I won't have anybody in 6-1. Now, the finite conductivity case, per our friends Cinco and Samaniego, and yes, I know I'm missing a line on one of the curves. You see the bilinear flow is given by the red dashed line. The linear flow is given by the blue solid line. What are the circles at the end, the lifesavers at the end of each one? And so nobody will accuse me of being an idiot, here's your other line. So what is this? This is the end of bilinear flow. Why does the end of bilinear flow have this strange shape? What causes the end of bilinear flow? The tip effect. Okay. It's just a conversation. There isn't any magic here or anything like that. It's just a conversation. Okay, so Cinco and Samaniego were under a lot of pressure to relate the radial flow case and the fractured well case. Now we already said that the effective wellbore radius, RWA, is equal to RWE to the minus S, right? So what's happening here is that when you plot RWE to the minus S divided by XF, look what happens, it goes to a half. For conductivities greater than 10, this correlation says that RW e to the minus F divided by, or e to the minus S divided by XF is equal to a half. So you can reverse calculate the skin factor based on that. Whatever the conductivity is, you can make that estimate. Give me a number. Pick a number. Let's say that it's 1. All right? So if it's 1, that's RW e to the minus S over XF is equal to what? Approximately 0.2, 0.2. Okay? Yes? Okay, what's your fracture half length? Give me a number. 50 feet? Is that a good number? Okay, so he's saying that we're going to calculate S. So RW can be equal to 0.25 feet. XF can be equal to 50 feet. What's e to the minus S? E to the minus S is going to be equal to 0.2 XF over RW. And what's that going to be? 40. Sorry, doing my side from here. So that's 50, 0.25. You say that's 40. Okay. What's that do wrong? Nothing. Okay, so that means that S is equal to the natural log of 40 to the minus. Somebody has a negative natural log of 40 handy in their brain. Anybody want to guess what the number's going to be? that's gonna be -5, -4. What would happen if it were a bigger, longer fracture half-length? Let's say instead of 50, it was 100, so that'd be 80, right? What do you think? Okay. So you're potentially gonna see some very large negative numbers for skin factors from fractured wells. It's the wrong flow configuration. You are making an approximation. You're saying that I want to get an idea of what this well would look like if I converted it to an unfractured well. That's what this concept is about. I don't know why they were doing this. I mean, I can imagine why, because people were very cold to integrating fractures into their vocabulary. They understood skin factors. A manager could say, we've got a skin factor of X, and everybody would nod their head in agreement. But now, you've got somebody saying, well, I'm going to put a fracture in this well. And their question is, well, what does that give me as a skin? And they weren't even used to thinking in negative numbers. All right, I'll give you an example. Those of you in Dr. Nasser-Al-Din's group, did he talk to you about skin factors? No? Okay. Well, we had a fella here about 20 years ago, John Gidley, whose picture's on the wall out there, and he was really into sandstone acidizing. He would take a case that was a skin factor of 200, and by sandstone acidizing would reduce it to 10 or something like that, okay? That's the same thing we're looking at here, but what we're talking about is you can have exorbitantly large numbers, positive numbers. But how do you convert that to an equivalent fraction? It would take an ocean of acid. It would take some mechanism that doesn't exist to do that. Okay, now let's talk about natural fracture. How does rock break best?
Along the path of...
Okay, so you can beat on rock with a hammer. But why don't you put it into a cell and try to pull it apart? What happens when you pull it apart? Is it going to break? If you have a compressive load or a tensile load, where's rock going to break the easiest?
Oh, perpendicular to the structure.
Compressor.
No, rock is much less strong in the tensile. Okay. You don't know that because you don't imagine pulling rock apart. But you can push rock together in the tens, hundreds of thousands of psi. But you pull on it just a little bit, it's going to break. So rock fracturing is actually thought to be preferentially a relaxation event, like that. And that's what I was saying yesterday, is we're not sure what's going on with microseismic. You know that you're pushing, because that's the whole point. But does the rock break as you push it, or does it shear? That's the other thing. Is it shearing, or is it breaking in some other fashion? Do you remember when you took your, what was it? Let's start the push it. My apologies. Do you remember your mechanics and materials class? You didn't have one. Bend it. What's going on the top? It's screaming, you're trying to tear me apart! What's going on the bottom? Oh, you're squeezing the crap out of me. Reverse it. Where's it going to break first? It's going to break in tension. Okay? Same thing with rock. Look at the diagram. Now. Okay. Rock doesn't mind being in compression. It does not like being in tension. Okay, so naturally fractured reservoirs. Where's one of the most famous naturally fractured reservoirs in the world? What about in Venezuela? Dennis,
I know the Ferrera is still here.
do you like living in the past? A little bit? Did you like dinosaurs?
I was a fan.
Hmm?
I was not a fan of dinosaurs.
Really?
Yeah.
Is it in Mexico? Utah? Arizona? Yeah.
We're probably gonna stumble onto something I don't wanna know here. Because we're using Bing. Where's Google? Would you please change your default browser?
I am not that naive at all.
Okay. You should never ever use Wikipedia. Alright, so it hit here. This is not a joke. This guy actually did a gravimetric survey, I know it's an artist rendering, and found it. So I was teaching a course down in Mexico, and they all started telling me about their naturally fractured reservoirs, blah, blah, blah. And then they told me this was what caused it. I laughed so hard I had to change my diaper. You need to learn from other people's mistakes. This is what caused the natural fractured reservoirs in Mexico. Of course, it pulverized whatever it hit. The reservoirs are where are most of Mexico's reservoirs? Okay, so it was over here. Where's Mexico's primary reservoirs? They're here, Veracruz, Villahermosa, and Ciudad del Carmen, which is actually over here, and right where my mouse is, and then up here in the Puerto Rico region as well. There's actually a reef trend that is an offshore sequence of reservoirs as well. But this thing hit somewhere over here and it smashed everything. What are these islands? I never noticed those before.
Could be smudges.
Yeah, could be. Good thing you brought that up. Why does this thing keep going to Bing? Where else has naturally fractured reservoirs?
Oh, that guy's face.
You don't know that guy? Okay, so you've got all of these reservoirs down here in Abadan, Aguas, and then offshore as well. You've got a few over here. What's here? So the reservoirs are over in here, and this mountain building caused them all to get crushed. So Mexico and Iran have a preponderance of naturally fractured reservoirs for completely different reasons. Can you think of other places?
Russia? Siberia?
Those are all things. These are carbonates.
Alaska have any? Alaska?
No, they're all sandstone wells. Think about the depositional system. It's all fed by rivers. So where do we have a carbonate reservoir nearby? Johan? Sorry? Hugoton, yeah, that's a chalk reservoir. It's not naturally fractured, but it's really shallow and it hasn't been. It might be naturally fractured, but it's not dominant. Yes?
Well, I don't know names, but it should be in the middle of the country because in the United States the middle of the United States was a shallow sea during dinosaur time. So.
There's something around that Appalachian Mountain.
Thank you, Mr. Spock.
Austin.
You're on map now.
Okay, this is probably the easiest. Here's the Austin Chalk mapped in Texas and Louisiana. The problem is in Louisiana it's really, really deep. It's along with Tuscaloosa, which is extremely deep and hot. Tuscaloosa is probably 20,000 psi, 400 plus degrees Fahrenheit. This is nasty stuff. We don't have much that can work in that environment. Okay, but over in Texas, where's the Austin Chalk? As you're driving around town, the wells that you see, they're all Woodbine, the one with the pumping units. They're well above the Austin Chalk. The ones that are gas wells, those are probably the Austin Chalk, the ones that don't have a pumping unit. And the reason that they're gas is because the window between oil and gas is here in Brazos County, over in Burleson County on the other side of the river, it's oil. When they first started drilling this with horizontal wells, they literally achieved the highest gas rates in history in the continental U.S. Why? Because the fractures look exactly like that diagram. They're not big enough to stick the finger in, but they're huge. And they occur in what's called a swarm. So it's sort of a nest of fractures like that. And if you're lucky enough to be in the right direction with your horizontal well, there were 40, 50 million cubic feet per day gas wells. Millions. However, natural fractures are often difficult to see and even more difficult to predict how they're going to perform. Now you can look at outcrops, and that's what geologists specialize in. There's a monograph on core analysis, and what's its very first line?
Geology in exact science?
No, it says, the only thing we know for certain about the core sample being analyzed is what? This particular piece of rock is no longer in the reservoir. That's how they started a book on petrophysics. So, being able to see natural fracture effects, you know, the geologists that go out and they do field studies, and they see all these joints and breaks and everything else, but that's at the surface. That's after it's been weathered. That's after it's been shifted. What's it look like downhole? What do you think? You've got 2 miles of overburden. Do you think you're going to see fractures you can stick your finger in? It'll be the rarity. All right, there's 2 models for natural fractures. There's 2 primary models. One model is a repetitive element of where each element is its own little reservoir. And what happens, the way that works, is you're able to represent the flux into part of the element. Both elements are full little reservoirs. They're treated as that. The other approach, the much more famous approach, is the sugar cube model or the Rubik's cube model by Warren and Root. You got this, Sam,
Slowly.
see the sugar cube model, the Rubik's cube model? The cubes are the reservoir, and the fractures are the spaces in between. Okay, that's all good and fine, but how does the fluid get out of the sugar cube and into the fracture? That's the trick. And so what Warren and Root did is they borrowed this concept from Barenblatt and Zeltov. They actually sort of stole it. But they came up with a really clever idea that Barenblatt and Zeltov missed, which was how to tie the fractures in the matrix together hydraulically. So a particle of fluid comes out of the matrix and into the fracture. How does that happen? How would you represent it? How would you represent the volume change? Well, a change in pressure equals a propagation of a particle of fluid. So it's like a mass balance. But then how would you model it as an equation of motion? This is a trick question. Anybody? So you're going to have something that looks and smells like the material balance equation to represent the mass transfer. And you're going to have something that looks and smells like Darcy's law to model the fluid transfer. They got really lucky here. The entire derivation for this is in my 620 notes. Maybe they didn't get lucky. I mean, maybe it had to work out that way. But they call it the pseudo-steady state interferosity model. Is it really pseudo-steady state? No. What it is the fluid transfer on a mass basis. For a change in pressure here, there's a particle of fluid that moves there. Where's that for us? That's in pseudo-steady state. So it's not a pseudo-steady state flow model, it is a pseudo-steady state flux condition. So there's a pressure drop and a particle of fluid move, and it's a 1-to-1 ratio. This model has a great deal of character in it. There's a lot of features in it. Whether it's right or not, I don't know. Here are the solutions for the Warren and Root model. And do you remember this? Where's the only one we're interested in?
It'd be the real main solution.
The second one.
So lambda and omega are what? If if omega is equal to 1, then it's a homogeneous reservoir case. So 1 minus 1 is 0, which is infinity in that argument, which drives that value to what?
1.
What's the exponential integral of infinity? It's 0. Okay. So if omega equals 1, this term goes to infinity, and this term goes to 0. Same thing happens here. This term goes to infinity, and this term goes to 1. But I didn't write that. Sorry. I'm really sorry. My apologies. It goes to 0. So these two cancel out, and we're left with a homogeneous solution. So really a clever idea. It's self-correcting. All you have to do is assume the behavior of the frame. The problem with this model is it's got so much flexibility. I didn't bring my flex curve. But this model is a mathematical flex curve. It can match anything. Up to and including and beyond what, Dennis? Things it's not supposed to. So if you apply this model to a heterogeneous system, that's what it was intended. If you apply this model to a homogeneous system, does it know the difference? No. Unless you tell it that omega is equal to 1, it's going to go out and try to find the best fit solution. And it may actually fit your data with the wrong part of the model. How do you sleep at night? I told you, I've sat through 2 defenses in this department, not my students, both of whom fitted non-fractured data with a fractured with a fractured reservoir model, and stood in front of God and everybody and said, "This is fine."
Did you fail then?
I just keep my mouth shut. I just smile. Unless you're my student, you're somebody else's problem. You know, when I was over in Mozambique teaching last month, this guy was telling me, he says, "You guys got it easy in the real world." He says, "You buy something that breaks, you take it back to the store and they give you another one." He said, "We buy something that breaks here, they go, you should have known better." In other words, they're not responsible. Is that how things are in, where are you from then? Illinois?
No, Texas.
No way. So here are the traditional reservoir models: vertical well, infinite acting, radial flow, vertically fractured wells, infinite conductivity, finite conductivity, naturally fractured reservoirs, pseudo-steady state, interporosity flow, transient interporosity flow, and then last is horizontal wells, and we didn't cover horizontal wells because horizontal wells are just too damn hard. I admit I'm lazy. It's just too hard. What are the possible flow regimes you'd have in a horizontal well? Early radial flow around the well, later linear flow to the well, and then maybe a secondary radial flow. Now, when you apply hydraulic fractures to it, that adds several more flow regimes.
And we couldn't get 1/3 from any of them?
Let me tell you what I think, all right? I'm going to do you a favor, and I'm going to show you what I think.
I'm still going to say that 1/3.
Hold your water.
Oh. I remember thinking.
Okay, so now what he's done is he's put horizontal and vertical fractures together. And now you get 1/3. You have the 1/2 here and the 1/2 there. And so I thought I'd pin the snipping tool. Why'd you unpin it?
I didn't. I think the computer automatically did it.
Hmm?
I think the computer automatically did it.
No.
Yeah, I'm
Every
logged
bad carpenter blames their tools. We already talked about that.
I'm logged in on a different computer and saved that profile out.
Thank God you're a lawyer. All right, so I'm going to grab a line. Okay, there's half float.
Sure.
That's half. You like fat line?
That's too big.
You don't know that's too fat. So there's your linear flow, and there's your linear flow. All right? So let's steal this line. 1/3, roughly. Okay. So it's just a thought. I've got nothing else in my bag of tricks. This is the one time where I tell you all my secrets. I got nothing else. I cannot think of anything else that would cause a 1/3 slope. I even looked at a case today that had a 1/3 slope. Somebody first showed me a 1/3 slope with a vertically fractured well probably 15 years ago. And I'm guessing maybe it was in a dual porosity system, but I don't recall that. I don't recall that. Now, in a shale, it might be possible, maybe, to have these horizontal fractures. How could that happen? How could you have a horizontal fracture?
There's a fracture create and a fracture that's naturally already there.
Are you comfortable with a physical exercise? Are you afraid of me? No? Put your hands together like that on the floor or on the table. No, like this.
Okay.
Pick me up. Damn, boy. All right. Now try. All right. Turn them sideways. Put them down. Now open your hands. Okay. So which way is easier? Okay. So fractures propagate how? Perpendicular least principal stress.
Yeah.
What's the maximum stress, Sam, dude? Old fatty standing on your hands, huh? So how are you going to lift the earth? Anybody? Like this, it's going to propagate vertically in one direction or another. Like this, it's going to propagate horizontally. Okay? For shallow cases, we think less than 2,000 feet, you're probably getting horizontal fractures. But we're down at 13,000 feet. How are you creating horizontal fractures at 13,000 feet? I'm going to give you guys a lesson that you hopefully will never forget. What happened here?
Natural fracture.
No. Don't talk. Just what happened. This is called poker chicken. You guys want to be drillers, huh? No. Where's the drillers today? They don't show up. I talked about something. This is core cut out of the formation. Between each one of those was what? There was this white stuff. And that drill bit, when it comes along, what happens? It sheared it loose. That white stuff is like the stuff in between Oreos. Does that help? It's a carbonate skeletal material. There were periodic balloons. It exists, or its cousins exist now. You can see it from satellite photos. There was a satellite photo of this offshore of England. There was it's like an algae. It's not an algae. It's an organism. So they have these balloons. They die off. They fall to the ocean bottom, and they make a layer. They don't have any strength. When you fracture, I gave you a possible trick, not necessarily what's happening. But the rule we had about lifting the earth, that's still maintained. But what happens if the material holding it together has no integrity? And does it have to propagate very far? No. So you could have a primary vertical fracture and a whole bunch of horizontal fractures. And that could, I'm just saying could, give you a signature, like we just saw. From the simulation says it could. Now I know you're going, why the hell are you beating us up over this? Because whenever something is out of the ordinary, you need to be able to try to explain it. And in that case, if we start seeing more and more of this one-third behavior, you need to be able to explain it. Why? You may decide you're going to change how you drill. You may decide how you're going to change how you stimulate. These are billion-dollar questions. Okay. All right, so now these are all of the different type curves that we may deploy for analysis. We're going to change, okay, I'm going to hypnotize you. Forget everything else we talked about, okay? We're going to talk about these type curves and then quickly go over to PA. This one we've already looked at. Any questions about this? The assumptions here are radial flow. Oops, sorry, I already screwed this up. Radial flow into here. What's the reservoir boundary look like? It doesn't matter, it's infinite. Okay? All right, what's next? Okay, these are all rectangles. Each one of these is a rectangle with the well in a different place. There's a geometry issue. They should all have a pseudo-steady state decay, and they do. But the behavior of the pseudo-steady state decay is dependent on the geometry of the well. Okay. All of these, after this line, all of these have a Muscat exponential decay. This is pressure. Okay. So if you have a buildup that is long enough, then you should be able to see this decay trend. All right? Where's the bounded circular reservoir, the bounded square reservoir? It's here. So there's your symmetric solution. This would be this or this, whichever one you want to do. Okay? It's your sort of guide. In your career, how many times are you going to get to use this? None. This is like a special blade on your Swiss Army knife.
May also fail.
No, you may never use it. You know, you've got a Phillips head screwdriver, a flathead screwdriver. You've got those funny looking hex head square things. You've got a torque screwdriver. Maybe this one is a tie screwdriver. It's got 3 instead of 4 Phillips heads. You never have a use for this thing until you have a use for this thing. I would be one of the best, never see this applied in practice. Unless you go to Ramco or to Statoil or somewhere where they do a lot of build-up tests and high permeability systems, and you just have to see it. But if you're going to work for Smith & Jones Oil Company, you're never going to see it. That's not to say that we shouldn't look for it. Okay? Same here. Unless you are in a region where you expect to see a fault, do not use this. I told you this yesterday. The single fault case looks exactly like what? It turns out it looks exactly like transient interporosity flow for a dual porosity case. That's number 1. It also looks like an incorrect production time. What do you mean, Tom? I mean that if you give your calculation the wrong producing time for a pressure buildup test, it is possible to generate this signature. What the hell? You mean that by having an error in the data, that when you process it, you could get completely the wrong interpretation? Yep.
Exactly the same.
It can look exactly like that. You kind of have to play with the solutions, but when you look at the buildup case and you modify the time, it looks exactly like modifying the distance. So look at the buildup equation for distance and look at the buildup equation for time. The potential for them to look the same is just how you manipulate the parameters. Do you see what I'm saying?
Yeah.
There's a geometry component for the one where you've got
Instead of adding
the superposition.
time.
Okay, let me be very specific. Superposition in space is one completely different thing. Superposition in time is another completely different thing. But they have the net effect of causing you to add a pressure drop.
Yeah.
This case, under certain circumstances, it generates that. Or sorry, under all circumstances, it generates that. This case, if you put the wrong time in it, it'll generate that. Okay? Two parallel faults can look the same as a fractured well. You've already seen that. A fractured well has linear flow. A fractured well has exactly this. Now, you're not going to make a mistake like that, because if you've got a fracture, you know you're going to have a fracture. I want to warn you that fault signatures, F-A-U-L-T-S, faults, they happen a lot in large offshore reservoirs. And I'm not sure why. It could be that you do have subseismic faults appearing in your data. I don't know that. But it could also be that the rates are so poorly measured that that's what it comes from. Okay, now we've also talked about this at great length. This case has what? No wellbore storage. So can you ever use this? You can if you have low storage and you want to orient yourself. But what's going to happen, as you can imagine, is you're going to see the storage signatures do like this. And you're going to miss most of this. Okay? So the right answer is that we come along, and like I said yesterday, we take one of these curves and we make a wellbore storage case out of it. We take another one and we make another case out of it, and so on. And that's what's on the next slide. So here, sorry, the next slide. We take the low conductivity case, SCD of 1, and that's a single curve from the previous case. It's this one. We take this curve and we then go generate a bunch of wellbore storage solutions out of it. That's how that works. Okay, so that's that case. There's no relating this to that because all these have been distorted by wellbore storage. Now typically you do not see the large hump in the derivative for a fractured well. Okay? That's one pretty good signature. But you may also see no hump down here. There's no hump. Another issue is a lot of people see this and they think that's radial flow. Radial flow is over here. I know you're going, I'm not going to make that mistake. But a lot of people do. They misunderstand that this is just an artifact. It's a transition artifact. There's no data, there's no information to be gained from that. This is the medium conductivity, and again, you can see the difference in shapes. And then the high conductivity, and you can see the difference in shapes. Okay?
Why do we still have labels?
Sorry, one at a time. Go ahead.
Why do we still have different label for different CDF on this plot?
This is CDF, not CFD. CFD is a top. Thank you.
Oh.
This was back when I did something really stupid. I listened to SPE. SPE changed the symbol for SPD to CFD, and then they changed it back because they made it so confusing. And there's probably one or two on here, Sam, that are not, that I didn't catch, that are backwards. But you're absolutely right. You know, anybody in their right mind would be confused by this. So you've got CFD as FCD, and then you've got, CFD is FCD, and then FCDF is source code. Good God, that's confusing. Okay? And then this is the dual porosity type curve with the pseudo-steady state model. Abhishek, what does this disk tell you? When does the derivative go to zero?
When the rate changes.
When it's
Rate
flat.
of change is constant.
Okay? So it changes from your perspective, it changes from the fracture system. There's a transition where it's flat, and then it changes to the total system. That's what happens here. And the more contrast in the sortivity between the fracture system and the total system, the flatter it is. So that's what it's telling. And if it were not dual porosity, it would just be a constant, and then it would be straight across the top. It would be equal to half.
But W could be seen as omega could be seen as the fraction of the volume that is the fracture, right?
It is the volume of fluid that is stored in the fracture, but it also includes the compressibility term. So it's not quite, it's an element of how much energy would be stored in the fracture system. And you can imagine it would be very little if the fracture system is small. But that will still have a great deal of influence on it.
So then why would the smaller values of omega have a bigger skipping effect?
Well, the bigger values would be closer to being homogeneous. That's the way to think about it. The higher values of omega would be, so this is a deviation from homogeneity. So it switches from one to the other. If there's no switch, then it's just is constant. There's a little bit, and so on and so forth. So the more severe the differential, the more severe is this behavior. Okay, and then the next one is something we did not cover, but this is transient interporosity flow. A transient interporosity flow has a fundamentally different shape. Why? Because here, the condition of where a particle of fluid leaves the matrix and goes into the fracture is governed by a time-dependent equation. Now, Arietta and Deschwann, they were looking at the pseudo-steady state condition. They said, this is wrong. This can't be met in practice. So they derived a transient exchange model. Which one is more likely to be seen in practice? The irony is, you can't say. These are both idealizations. You probably see one about as often as you see the other. Okay? Dennis, does that make sense? Even though we've got the condition wrong, you probably see one about as often as you see the other. Is that okay?
I think so.
Okay, and here's where we hit the hallucinogenic part. I can't tell by looking at you guys what your nature's gonna be, but this was created by a student of mine from Colombia, and he was, introverted, you know, introverted, yeah. He, had the entire room running these curves during the summertime. He commandeered all the computers. It was running on Mathematica. And somebody came in and restarted one of the machines and killed one of his jobs, like you all do. You put a piece of paper on it, you know. And he could have just gone across the hall to the other rooms, and instead he sat down and killed one of his runs, and, you know, really messed up his sequencing. And he comes to me and he goes, "What is the penalty for murder?" I said, you know, you need to just let it go, just rerun it, no problem, you know, live and love and everything else. And he goes, "No, I am Colombian, it must be dealt with." Oh my God! And I bet you, if we contacted him right now, he would still know what day, what time, what the guy's name was, and probably, you know, have him buried up to his nostrils in cement, you know. Any rate, don't log somebody out if they're logged in doing research runs. You guys do that anymore in the common areas?
No,
I
they
still think
usually have
people-
paper on the computer.
Hmm?
Usually just have a paper.
Yeah, I know, but this guy just, he didn't feel like walking across the hall, so he just restarted the computer and, oh, that was good. What is the penalty for murder? You can't afford it. So, what he was looking at was varying lambda. So that's what you're seeing here is a variation in lambda. There's more to it than that. But, what do you get the feeling of? If all you're varying is one parameter here, and you drastically change the nature of the shape, what does that tell you? It tells you you don't want to play around with this model unless it really applies to your system, because you'll match anything with this thing.
What does lambda represent?
Lambda determines, omega is how much the sortivity ratio is, lambda is how it interacts with each other. So, how early or how late.
It doesn't change that low, it's a log.
Yeah, it's a log space. So lambda would be the duration or the event, and omega would be the relative magnitude of the same kind of thing. I'm telling you, this guy generated several hundred runs doing this. Maybe even thousands of runs doing this. You just don't find that kind of commitment today, you know.
Is he the 6-part pieces?
No, it was another guy. That guy was even crazier. I mean, I'm a magnet for these kind of personalities, I gotta say. The guy that did 6 volumes, he was not gonna be stopped, you know, in his dissertation. And another one of my guys, we met for his prelims, and we told him he had 7 elements of his dissertation, each one which could be its own element. They all became their own papers and that sort of thing. And he insisted that he wanted to do the last 2, and the committee told him no. And we said, well, you know, if you want to do this, we're not going to stop you, because it's going to cost you an extra 2 years. He said, that's my business. You just don't meet people like that. You know? And he was working at the time, and he did this at night, weekends, and that sort of thing. Just incredible. Okay, any advantage of using type curves instead of interactive models? This is where me and Mr. Jose at Kappa, we go to Fifth City by way of Knuckle Junction. You guys know that saying, right? We're always going to fight over this. He says over his dead body, will he ever use a type curve? But the nice thing about type curves is your brain makes an image of it. You're never going to forget this image. But now, if you're looking at just a computer model and you're playing with omega, does your brain know where the next move is? No. That's the problem. I mean, unless you train yourself in optimization, you've got to understand when you've got 4 or 5 parameters that are changing, which one's going to go where. And by the way, if you're going to use regression, there will be a disease in your family caused by you doing that. That's like a sin. Okay.
Regression? Regression?
Regression. Yeah. Regression should only be used after you have a match and you want to refine it. If you walk up to the software and just push go, I want you to imagine me for the rest of your life. You're going to be in my class, and the exams are just going to get harder, and the stories are just going to get worse, you know, for the rest of your life. maybe for an eternity in your case, Joe. So do not use regression. Okay, what is the best diagnostic? The pressure derivative was the 1980s. I told you everybody claimed ownership of that. The pressure integral functions, 1990s, that never caught on. And then the beta derivative, which was identifying power law regimes. Why are power law regimes important? Radial flow is not a power law regime. But radial flow, the Ford A derivative identifies radial flow. But we needed something that would tell us where a power law, can somebody name a power law regime? Sure, the quarter slope and the half slope, those are power law regimes. So if by using the beta derivative, you see that, you know, there's 3 orders of magnitude or data or constant with the beta derivative, that tells you that that was pretty useful to identify a power law regime. Okay, I think I'll stop here, and tonight we'll pick up on PA, and so I'll see you then. Dennis, can I rely on you to log out?
Yeah.
Or I guess I can. Sam, do you have any preference on what kind of problem to have?
I'd really like to work on the actual data and try bidding, finding stuff. We didn't get to do that on the team.
Okay, yeah, we'll definitely do that. Sam, too, do you have any kind of case you want to look at?
No, off the top of my head.
Dennis?
Nothing I can think of.
Horizontal well?
I don't want to go to that.
Let's see what we can do. All right, everybody have a safe day. I'll see you next hour.
Oh, yeah. See you on Thursday.